Hello everyone, this is Professor Kuehn. Today I will be talking about Chapter 7 of A Student's Guide to the Great Physics Texts. This chapter is entitled Beams, Bones, and Giants, and it is the last chapter that Galileo is focusing on the strength of materials. You might recall that in the previous discussion, which was from the second day of Galileo's dialogues, Salviati, Sagredo, and Simplicio found that by using the law of the lever, one can conclude that the transverse force required to break a beam extending horizontally from a wall depends on the beam's length and diameter. In particular, it depends on the length and diameter in the following way. I'll draw a picture of this. So you have a beam sticking out of the wall, and if it has a length L and a diameter D, and we're asking how much force does it take, how much transverse force does it take to break it, the transverse force required to break it scales as the cube of the diameter divided by the length. That is, by doubling the diameter, you increase the transverse force required to break it by a factor of 8. And if you double the length, you reduce the transverse force required to break it by a factor of 2. So again, this is the transverse force required to break this beam. And that concluded Chapter 6 in A Student's Guide. You might remember kind of where this comes from. Let me just give you a short reminder. A beam breaks when the braking moment that's trying to make the beam rotate in a clockwise direction about the fulcrum exceeds the supporting moment, which is trying to hold it up and keep it from rotating. So it's kind of a counterclockwise directed torque as opposed to a clockwise directed torque. And you might recall that, so basically this breaks when the supporting moment is less than the braking moment, right? So I guess the borderline case is when they're equal to each other. And the supporting moment, that was proportional to the longitudinal resistance and the lever arm d over 2, right? So this was this lever arm right here, and there was a resistive force that was holding it together right here. So the supporting moment went as that resistance, the longitudinal resistance, and that the lever arm, and the braking moment goes as the transverse force and the length, right? And then you might remember that this longitudinal resistance, this was proportional to the square of the diameter, or the area, and so we get 2 factors of diameter that come in there, and we get 1 factor of diameter that comes in here. And you'll see here, if we relate these, this is where we get that the transverse force it takes goes as d cubed over L. So this is just a quick reminder. You might want to go back and look at this derivation, but this is a quick aside or a reminder of where we found this formula right here. Okay, so that's by way of review of Chapter 6. Here's the question that we're moving on to now in Chapter 7. So this is Chapter 7 starting here. Okay, so let's go back to one of the original questions that Galileo asked at the beginning of day 1 of his dialogues. And here was the question: can structures or living organisms be scaled up, so to speak, and retain their structural integrity, and still retain their structural integrity. That is, i.e., their ability to stand up under their own weight. Right? Or is there some kind of size limit? What animated Galileo's interest in this, or what kicked off his interest in this, I suppose, was his analysis of the text of Dante's Inferno. He did a structural analysis of hell in his Inferno to see whether Dante's reported structure would be able to stand up under its own weight or whether it would collapse. It was an interesting theoretical question, but it led to deeper questions about the maximum size or scale of built structures or living organisms. The answer at which he arrives is simply no. Things cannot be simply scaled up infinitely. There's going to be some limit. So this is the answer. Now let's motivate how we know this to be true. So let me give you a simple example that will steer you in the direction of how we're going to answer this question. So consider a beam sticking out of a wall if it's increased in size. So if a beam projecting from a wall is increased in size, eventually it gets to a size at which it will collapse under its own weight. It will get to a size at which it will collapse under its own weight. Okay, so let me draw a picture of this. This is the same kind of picture that Galileo has been using all along. So here's a wall, here's a beam projecting from a wall, and let's suppose that it's got a diameter d and a length L, like this. And then we imagine that its weight, I'm going to draw its center of gravity right here, and there's a weight that is trying to break it. That is, it's creating a torque about this point that is trying to snap it. Okay, and just as for your information, this that we're talking about is Galileo's Proposition VII on page 92 of the text. Okay, now what happens if we scale this up? Okay, so imagine we're just going to increase the diameter and the length in by the same factor. What is going to happen? Okay, eventually, when you do this, let's say double or triple or quadruple the length and the diameter, what eventually happens, so if you go, let's say you go to 10 times the diameter and 10 times the length, and it's got a new weight, so let's say whatever that new weight is right here, eventually it's going to get to a point where its weight makes it crack. So it's going to split right in here, and it will fall, crack, right? It will fall under its own weight. That's the claim that Galileo is making. Now let's ask why, see if we can get an intuitive understanding of why this would happen. I suppose you believe this already. Maybe you don't, but maybe you do. Believe this already, but is there a way we can think about this that would justify our intuitions? So question, why does this happen? And the answer that Galileo arrives at in the course of this proposition is that the braking moment depends on the weight and the lever arm. So we can figure out how that braking moment scales with size. So the braking moment that we had talked about before, the braking moment depends on both the weight of the beam, and the lever arm, which is related to the length of the beam. Right? So if we think about the braking moment, how does the braking moment, remember, that's what's trying to make it rotate in the clockwise direction about the fulcrum. Well, it depends on the weight, the product of the weight and the lever arm, which is L over 2. And the weight, remember, the weight of this beam depends on the overall volume of the beam. It's proportional to the volume. So if we want to ask how the braking moment depends on the various dimensions, it's proportional to the weight, which depends on the length times the square of the diameter, right? So this is, because it depends on the volume, the square of the diameter gives you the cross-sectional area, the length gives you how long it is, of course, so that's going to show how the weight depends on these dimensions. And this, of course, depends on the length. I'm dropping factors of 2 and factors of gravity and so on, just to give you a sense of how this depends on the various dimensions of the beam. So the braking moment goes as the diameter squared times the length squared, right? But what about the supporting moment? I'm going to move this over to here so it's out of my way. The supporting moment, remember, that is caused by the longitudinal resistance that is trying to hold this up, right? And this lever arm right here. So there's one lever arm, here's another lever arm right there. So the supporting moment depends on the longitudinal resistance, R, right? And the supporting lever arm. Right? So if we wanted to write down a proportionality for this, so the supporting moment, again, is trying to hold it up, that's proportional to the longitudinal resistance and the supporting lever arm, which is going to be proportional to the width of the beam. I could put d over 2 if I wanted to, but we're just interested in not factors of 2, but rather these dimensions here. And the longitudinal resistance right here, that depends on the cross-sectional area. So it goes as the square of the diameter, and this goes as the diameter. And so overall, the supporting moment is proportional to the cube of the diameter, right? So we're getting a sense of how, as you scale the beam up, how the supporting moment changes and how the braking moment changes, right? Now, notice that as you increase the size of this object, let's suppose you were to double the diameter, double the length, and so on, you're keeping the ratio of diameter to length the same, but you're just increasing them by some factor of 2 or 4 or 8 or 10. There are 4 factors of size that come in here, 2 diameter and 2 length. So we've got 4 factors of size that show up in the braking moment, whereas we've only got 3 factors of size that show up in here. Right? So in other words, the braking moment is going to increase more rapidly than the supporting moment as you increase the size. And that's the most important point, is that the braking moment increases more rapidly than the supporting moment as the size increases. Right? And so at some point, even if it's going to be able to support its own weight at a small size, at some point it will get to be a large enough size that it will in fact break under its own weight. So this is one of the main points that Galileo is getting at here, and this is precisely why he says things like, well, if you look at the mast of a ship, right? The mast of a ship, it's got some horizontal beams sticking out that are supporting the scales, and if you have those horizontal beams to be a certain size and they support the sail and they support their own weight, you cannot simply make the ship 3 times as big or 5 times as big or 10 times as big, because at some point those horizontal beams that are sticking out of the mast, they will eventually have a larger braking moment than their supporting moment, and they will collapse under their own weight. And this has implications as well for the size of living organisms. So we'll say a few more things about this when we get together next time.